Hello guys, welcome to H₂O, the A to Z of chemistry. I am Dr. Ritu, your educator for this course, Basic Concepts of Chemistry. Today we will begin with lecture 10 from the course, but make sure you have watched the previous ones before viewing this one. In this lecture, we would be discussing about solutions. Why solutions? Because most of the reactions that we are going to do in the laboratories, they are going to be performed in solution form. So it is essential to know what are solutions and then what are the concentration terms we use for the amount of substances which we use to make these solutions. So starting with the definition of what is a solution. Well, solution is a homogeneous mixture of two or more pure substances whose composition may be altered within limits. And I hope you remember what is a homogeneous mixture. We did discuss this while we were classifying matter into mixtures and pure substances. Quickly revising, mixture contains two or more pure substances present in any ratio which are called its components, and a mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components they completely mix with each other. The composition is uniform throughout. For example, we have a sugar solution, and then a heterogeneous mixture, the composition is not uniform throughout and sometimes different components can be observed, right? So solution hence is a homogeneous mixture. So it consists of two or more substances which are uniformly mixed with each other. Generally, a solution is composed of two components, and such a type of solution which has two components is called as a binary solution. And this consists of two components. They are the solvent and the solute. So what is a solvent and what is a solute? Well, solvent is that component of the mixture whose physical state is the same as that of the resulting solution, whereas the other component is called as the solute. For example, in the sugar solution, we have sugar and we have water. So water has the same physical state as the resulting sugar solution. So that is the solvent, whereas sugar would be the other component, that is solute. So now you can ask that if the physical state of both the components is same, then what do you say? So well, the component in that case which is in excess is called as the solvent, while the other is called as the solute. So example, you can have that of alcohol and water, and alcohol and water, they are miscible in all proportions. So if you take more of water, then water would be the solvent, and if you take more of alcohol, then alcohol will be the solvent. So the one in excess is the solvent. So now, as most of the reactions occurring in solutions, we should know what is the concentration of a solution. It is basically the amount of substance present in its given volume, and this can be expressed in a number of ways. These include mass or weight percentage, which is denoted by percentage W by W. Then we have weight by volume percentage, percentage W by V. Volume by volume percentage, percentage V by V. Then we have mole fraction denoted by the small x, molarity denoted by capital M, molality denoted by small m, and then finally we have parts per million, which is ppm. So we will understand them one by one. First we have is the mass or weight percentage, and this is defined as the mass of solute in gram per 100 gram of the solution. That is, this is equal to mass of the solute in gram divided by mass of the solution in gram multiplied by 100. For example, if we have percentage of NaCl solution to be 5% W by W, this means that the solution contains 5 gram of NaCl and 95 gram of water, because the mass of the solution is 100, right? As the mass of the solute per 100 gram of the solution. So 5 gram if it is solute, 100 gram is the solution. So weight of the solvent water would be 95 grams. So this is 5 over 95 plus 5 multiplied by 100, making it 5%. Then we have weight by volume percentage. So this is percentage W by V, and this is defined as the mass of solute in gram per 100 ml of the solution. So this would be mass of solute divided by the volume of the solution multiplied by 100. Now, if we have 20% weight by volume HCl solution, this would mean 20 gram HCl present in 100 ml of the. Next we have volume by volume percentage. So this represents basically the volume of the solute present in 100 ml of the solution. So this would be again volume of the solute divided by volume of the solution into 100, all in ml. And if we have a cough syrup on which it is written 5% V by V of alcohol, it would simply mean 5 ml alcohol is present in 100 ml of the cough syrup. Next we have parts per million ppm. So this represents the mass of solute present in 10 power 6 grams of the solution. So this would be mass of solute over mass of solution into 10 power 6, mass of the both solute and solution being in grams. And then this unit is used to express the concentration of very dilute solute. For example, we have, suppose 500 ml of water containing 2 into 10 power minus 3 gram of chlorine. Now 500 ml of water is equivalent to 500 grams of water because the density of water being 1 gram per ml, right? So if we are supposed to now calculate the ppm of chlorine in this water solution, so this would be 2 into 10 power minus 3 divided by 500, which is the mass of water, right, multiply by 10 power 6, and this comes up to 4. Instead of the mass of solution, we have taken the mass of the solvent over here because the mass of the solute is so small that this can be ignored, right? So that is why we have just taken the mass of the solvent rather than taking mass of the solute. Now instead of ppm, if we express the concentration of chlorine in mass percentage, then it would be 2 into 10 power minus 3 divided by 500 into 100. So in ppm it is 10 power 6 and here it is 100. And this you will write as 4 into 10 power minus 4. So it is easy to write 4 than this 4 into 10 power minus 4. That is why for the very dilute solutions, we try expressing the concentration in ppm. And then we have parts per billion also similarly, where this would be mass of a solute divided by mass of the solution into 10 power 9 because 1 billion is 10 power 9. Next we have another very important term, mole fraction, and this is denoted by the letter small x, and this is the ratio of number of moles of one component to the total number of moles of the substances in the solution. So if we have to find the mole fraction of the solvent, let it be x1. So this would be n1 over n1 plus n2, where n1 is the number of moles of solvent and n2 the number of moles of solute. So for calculating the mole fraction, you would be dividing the mole fraction of the solvent or the solute, whatever you want to, and then divide it with the total number of moles of all the substances which are present in the solution. And if we have to find the mole fraction of solute x2, this would be n2 over n1 plus n2. And now if you sum x1 plus x2, this comes up to 1, and this is a very important result, that the sum of mole fractions of the components of the solution is always equal to 1. And now one more important point, that mole fraction does not depend upon temperature. Why? Because it does not have the term volume in its formula, right? If any concentration term has volume in the formula, then it would be dependent upon temperature, because generally the volume increases on increase in temperature, right? As mole fraction does not have the volume term, so it does not depend upon temperature. And this can also be extended to solutions having more than two components. For example, if we have three components, then the mole fraction of the solvent would be N1 over N1 plus N2 plus N3. And if there are four, then it would be N1 over N1 plus N2 plus N3 plus N4, and so on. Let us see an example. If we have a solution containing 36 grams of water and 46 grams of ethyl alcohol C2H5OH, then what would be the mole fraction of water and ethyl alcohol? For this, you are supposed to basically calculate the moles of both of them. So the moles of water would be 36 divided by 18, so 2 moles, and moles of ethyl alcohol 46 divided by 46, which is the molecular weight of ethyl alcohol, and this comes up to 1. So mole fraction of water would be 2 over 2 plus 1, this becomes 2 by 3, and for ethyl alcohol it would be 1 over 2 plus 1, this becomes 1 by 3. And now if you add both of them, 2 by 3 plus 1 by 3, this comes up to 1. So always remember that the sum of mole fractions of the components of the solution is always be equal to 1. Then we have molarity or molar concentration, and this basically, how do we define this? A substance containing 1 gram molecular weight or a mole of it per liter of the solution is said to be a molar solution. So the formula for molarity is moles of the solute divided by volume of the solution taken in liters. So if we denote the moles of the solute by NB and divide this by V, this is the molarity, and moles can also be written as the weight of the solute divided by the molecular weight of the solute and again divided by V. So this is how we can calculate the molarity of any substance. Now we have an example. If we have an NaCl solution to be 5 molar, this means that 5 moles of NaCl are present in 1 liter of the solution. Molarity is the most common unit used for expressing the concentration of a solution, and you can now also remember that since the term molarity has volume in its formula, so this would be dependent upon temperature. Next we have molality, the number of gram moles of the solute present in 1000 grams of the solvent or 1 kg of the solvent is called as molality. So the small m denoting molality is equal to the moles of the solute divided by mass of the solvent in kilograms. So the basic difference between molality and molarity is going to be in the denominator. For molarity, we have the volume of the solution in liters, and for molality, we have mass of the solvent in kilograms. So please always remember this. Most of the students confuse between the solution and the solvent, right? Either they take solvent in case of molarity also, or they are taking solution in terms of molality also. Please be very careful. For molarity, it is volume of the solution, and molality is the mass of the solvent. And the units of molality is moles per kilogram, and this is not going to be affected by change in temperature because there is no volume term involved. and this can again be represented as NB, the moles of the solute, divided by the weight of the solvent in kilograms. Moles of the solute, again you can write weight of the solute divided by molecular weight of the solute divided by mass of the solvent in kilograms. For example, if we have H₂SO4 to be 6 molar solution, so this means that 6 moles of H₂SO4 is present in 1 kg of the solvent, and had it been 6 molar, it would mean 6 moles of H₂SO4 present in 1 liter of the solution. Now, few points to remember for you. The concentration terms which have volume in their formulae, they are temperature dependent. I have already discussed this with you. So please always remember this. This is very important. The examples being percentage V by V and percentage weight by volume and molarity. And the concentration terms which don't have volume in their formulae, they are temperature independent. For example, percentage W by W, the mass percentage, mole fraction X, and the molality. Then, if you are given in a question that the strength of the solution is this much. So, what does strength of a solution mean? It simply means mass by volume. Okay, so the units are going to be gram per ml, gram per centimeter cube, kg per meter cube, kg per liter, gram per liter. So anything basically the mass divided by volume, mass of the solute, volume of the solution. So this signifying the strength of the solution. And then there are some important conversions for you which you have to remember because they are important while you are doing your numericals. So you should know the conversion between the centimeter cube and milliliter and so forth. So 1 centimeter cube is 1 ml, 1 meter cube is 1000 liters, 1 decimeter cube is 1 liter, and 1 centimeter cube is 10 power minus 3 liters. So please do remember them. You are bound to make mistakes if you do not remember them. And now I have a few interconversion formulas for you. These are going to be basically helpful when you are given the exact things. For example, if you are given the mole fraction and you have to find the molarity. So you can, rather than going through long procedures, you will realize that while you are doing the numericals, that if you are given the mole fraction and you have to find the molality, this formula would help you save time. Similarly, there are a few more interconversion formulas, so please do remember them. They are going to help you a lot. Do quick calculations because that is going to be very important key to your competition success. So here the terms small m is going to denote molality, right? So we have xp, this is the mole fraction of the solute, ma, the molecular weight of the solvent, d is going to be the density of the solution, mb again the molecular weight of the solute. Then we have m alone, capital M being the molarity. Then we can find directly a relation between molarity when percentage mass is given and density is given. So basically these formulas, they are going to help you. Just quickly do your calculations. So now we will do quickly a few numericals based on these concentration terms so that you understand the meaning of these concentration terms also and then how to utilize them also. So the first question says, what is the concentration of sugar in moles per liter if its 40 gram are dissolved in enough water to make a final volume up to 4 liters. So basically you are supposed to find the concentration of sugar in moles per liter. So this means you have to find the molarity because molarity is nothing but the number of moles divided by the volume in liters. So moles per liter. Now, to find the moles per liter, you have to find out the moles of the solute, and then the volume is already given to you. So we have mass of sugar to be 40 gram. The molar mass of sugar would be 342 grams. So you will get the number of moles of sugar to be 40 divided by 342. Divide this by the volume in liters, which is 4. So you get the molarity to be 0.0292 molar. Next, calculate the molarity of water if its density is 1000 kg per meter cube. Now you have to find the molarity. So you need the moles of the solute and you need the volume in liters. So we will move step by step. First of all, the density of water is 1000 kg per meter cube. So we can convert this meter cube into liters. First of all, we have 1000 kg divided by 1000 decimeter cube because 1 meter is equal to 10 decimeter. And 1 decimeter is equal to 1 liter. So you can write this as 1 kg per decimeter cube or 1 kg per liter. And this implies basically that in 1 liter of water, we have 1 kg of water. Right? So this is equal to 1000 grams. So you have the weight of water now. So you can find the number of moles of water to be 1000 divided by 18. So this you get as 55.55. Right? So the molarity of water would be the number of moles divided by the volume. So volume is 1 liter. So 55.5 divided by 1, you will get the molarity to be 55.55 molar solution. Okay. The next question we have is that 1.96 gram of H₂SO4 is dissolved in 300 gram of water. You have to calculate the molality of water. So basically you have the weight of the solute, you can find the moles of the solute, and then you have the mass of the solvent also. So you can directly put the formula of molality, which is the number of moles of the solute divided by mass of the solvent in kilograms. So mass of H₂SO4 is 1.96 grams. Mass of water is 300 grams. Molar mass of H₂SO4 is 98 grams. Number of moles of H₂SO4 would be 1.96 divided by 98, and then divide this by the mass of the solvent. You need that in kilograms. So 300 divided by 1000 to get 0.3 kg. So this comes up to 0.067. So the molality of this solution would be 0.067 molar solution. Now the question says, how are 0.5 mole sodium bicarbonate and 0.5 molar sodium bicarbonate different? It was just to give you again a realization, the difference between the various terms. So molar mass of sodium bicarbonate, if you calculate, is going to be 84. Okay, so this means that 84 gram of sodium bicarbonate is equal to 1 mole, and then 0.5 mole of sodium carbonate would be equal to 0.5 into 84. So this comes up to 42 grams of sodium bicarbonate. So this is basically the meaning of 0.5 mole sodium bicarbonate. And then we have 0.5 molar sodium bicarbonate. So 0.5 molar means the molarity of sodium bicarbonate solution is 0.5 molar, and that is simply meaning 0.5 moles or 42 grams of sodium bicarbonate are present in 1 liter of the solution. Next, we have to find the molarity of ethanol solution with a mole fraction of 0.020. Okay, so you are having the mole fraction. Put this in the formula of the mole fraction of the solute. So this would be equal to 0.02 equal to N2, the moles of ethanol, divided by the sum of moles of water plus moles of ethanol, right? So now the solution is very dilute. How do you get to know that? Because the mole fraction of the solute is very less. The rest is 0.98 is water. So this means that we have more of water and very little of the ethanol. So we can say that as the solution is very dilute, 1 liter of the solution would be equal to 1 liter of water. And now from this you can find the moles of water to be equal to 1000 grams, because 1 liter is equal to 1000 ml and the density of water is 1 gram per ml. So you can convert that 1000 ml into 1000 grams. So you have the weight of water divided by the molar mass, you get the moles of water, right? So now you can put the moles of water in this formula. So this would become 0.02 is equal to N2 over 55.5 plus N2. When you will solve for N, you will get N2 to be 1.13 moles, right? So now these many moles are present in 1000 grams of water, or you can say 1000 ml of water, that is 1 liter of water. So this means that the number of moles divided by the volume, which is 1. So molarity of the solution would be 1.13 molar solution. Next we have is to calculate the concentration of HCl acid in moles per liter, again the molarity, which has a density of 1.41 gram per ml and the mass percentage of HCl in it being 40%. So when we say mass percent of hydrochloric acid is 40%, what does this mean? It simply means that 100 gram of HCl solution contains 40 gram of HCl by mass. Then you have the molar mass of HCl, that would be 36.5. And number of moles of HCl in 40 grams, you can calculate this to be 1.096 moles. Now you are given the density to be 1.14 gram per ml. So what does this mean? That 1.14 gram HCl is present in 1 ml of the solution, and we have how much? We have 100 grams of the HCl solution, right? So volume of this 100 gram of HCl would be 100 divided by 1.41. This comes up to 70.92 ml, or you can convert it into liters by multiplying by 10 power minus 3. Then you have the concentration of HCl in moles per liter. So this would be 1.096 over 0.07092. This you would get as 15.44 molar. So I hope the things are clear to you. I have tried to put up all the terms which we had learned in these numericals. Next we have is ppm. So we have a sample of drinking water, and this was found to be severely contaminated with chloroform, and which is supposed to be carcinogenic in nature. It can cause cancer, and then the level of contamination was 45 ppm by mass. You have to express this in mass percentage, and then you have to find the molality of chloroform in the water sample. So we have 45 ppm. So this means 45 parts of chloroform in 1 million parts. And when you have to find the percentage by mass, you have to find this in 100 parts. So percentage by mass would be 45 divided by 10 power 6 into 100. So this would be 4.5 into 10 power minus 3%. The next you have to find the molality. So molar mass of chloroform is 119.5 gram per mole. So 100 gram of the sample would consist of how much chloroform? 4.5 into 10 power minus 3 gram. So this is what is the meaning of percentage. And if you convert these grams into moles, this would be 4.5 into 10 power minus 3 divided by 119.5, the molar mass. So you get these many moles. So now molality would be 4.5 into 10 power minus 3 divided by 119.5 divided further by the mass of the solvent, which we had 100 grams, and this you will again multiply by 100,000 so that you convert these grams into kilograms. So it would have been 100 divided by 1000. The 1000 goes up. So we have 3.78 into 10 power minus 4 molar solution. So I hope all these questions are clear to you. Try practicing as many questions as you can. This is a very important topic. So that would be all for this lecture. I hope you really enjoyed this lecture with me. So please do share in your comments, your suggestions with us by mailing us at h2ochemistry@gmail.com. You can even put that in the comment section. If you have any problems, that also you can tell us. We will try to be as helpful as we can. In the next lecture, we would be discussing the mixing of solutions, again a very important topic. So bye for now. Meet again to discuss mixing of solutions. Have a nice day. Enjoy yourself. Bye bye.